Swayam Prabha. Digital India. Educated India.
I welcome you all to the session of Thermal Engineering Basic and Applied, and the topic of our today's discussion is the thermodynamic analysis of SI engine. So, before going to have this analysis today, let us first review several processes, those already we have discussed, and then we can try to map those processes again in different thermodynamic planes, essentially to estimate the efficiency, because SI engine, that is the spark ignition engine, we had seen that we are supplying fuel, and at the cost of that fuel we are trying to get some work output, and we have discussed that the stored energy, that is the energy, the chemical energy which is remaining stored within the fuel, is converted to the internal energy of the gases inside the combustion chamber, and that internal energy is eventually converted to the work and which is available at the crankshaft. So, you can understand that again through several processes using this particular engine we are trying to have energy conversion, and since it is nothing but the conversion of energy from its one form to another form, we need to calculate the efficiency or performance. So, for why it is called thermodynamic analysis, because we had seen that if we just try to recall that, if we try to recall several processes, and then we will find that inside the combustion chamber, pressure and volume, and temperature of the working substance, these three properties are continuously changing. So, if we need to know what is the volume at the end of any particular process, then we need to know about several thermodynamic relations laws. From there we can quantify what would be the work output finally in terms of several thermodynamic properties. So, let us first review again several processes, those constitute together to form the cycle of SI engine, and to do that let us first draw the schematic. So, we can see this is a schematic depiction of a spark ignition engine. Of course, we did not show several components, but those which are required only to understand several processes. We have discussed that engine cylinder, so engine is piston is having to and fro movement between these two locations, that is bottom dead center and top dead center. And we had seen that there are two valves, intake valve and exhaust valve. So, when intake valve is open, exhaust valve is closed, piston comes from TDC to BDC, and that is the intake stroke, and in this stroke we are taking rather fresh charge is drawn into the cylinder. So, this is the intake stroke. Next stroke is exhaust is remaining closed, but when piston reaches at BDC, at the end of the intake stroke, this intake valve is closed, and rather intake valve is allowed to be closed, and then piston comes from BDC to TDC. So, the fresh charge which is there inside the engine cylinder, then that gets compressed. So, the fresh charge gets compressed in this stroke, and that is the compression stroke. So, when piston comes at TDC, that is at the end of the compression stroke, both valves are closed. What is done? This is the clearance volume that you can see. So, basically this is the volume. So, this is the clearance volume. Right. So, the compressed charge is remaining there in the clearance volume, and spark plug switch is on. So, spark is initiated, and this is the combustion that we have discussed, and it is because of this combustion that the rise in pressure and temperature inside the cylinder will be excessively high. That high pressure create a thrust on the piston face, and the piston comes again back to BDC from TDC, and that is the power stroke that we have discussed. Both valves are remaining even closed during that stroke, that is the power stroke, and that is also known as expansion. And finally, when piston is at BDC, that is at the end of the power stroke, then exhaust valve is allowed to open, piston again comes from BDC to TDC, and inside the combustion chamber combustion gases are, these gases expel out through the exhaust manifold to the ambience. So, we have discussed about all these four processes several times in previous classes. Now, you have understood that one stroke is power stroke, that is the stroke in which we are getting power. That means, if you try to understand out of these four processes, rather four strokes, only one stroke is power stroke because we are getting power. Remaining other three strokes are ideal stroke, and we need to supply power to the crankshaft. So, these all four processes are occurring, rather these four processes occur in a cyclic manner, rather these four processes constitute together to form the cycle of the SI engine. Because it is spark ignition engine, so combustion will not be completed until and unless spark plug switch is on. So, now let us try to map all these processes in two different thermodynamic planes, one is PV, another is TS. And in this, why we are trying to map all these processes in thermodynamic planes, because as I said, we need to understand several thermodynamic properties both at the beginning and end of each stroke, only to calculate the thermal performance or thermodynamic efficiency of this cycle, which is very important. Now, for the analysis of this part, for the analysis of SI engine, what we can do? We have understood the cycle, and this cycle it is not a though thermodynamic cycle, because at the end of the cycle all the working substance, which is nothing but several gases, and that will leave out from the engine cylinder. So, those gases are not cycled back into the process. So, it is an open cycle. So, it is better to say a mechanical cycle. So, for the analysis of SI engine, this cycle should be approximated with an air standard cycle, and the air standard cycle which is used for this particular analysis, that is for the analysis of SI engine, that is known as Otto cycle. So, German engineer Nicholas August Otto, who invented this cycle, and that is why this cycle is named as Otto cycle. So, let me write Nicholas August Otto, who invented, and to honor him, this cycle is named as Otto cycle. So, let us briefly process all the map all the processes in thermodynamic planes. So, first is PV, another one is TS. Why are going to have TS? Because you know that we are trying to understand what is the power output, what is the work output at the cost of some input energy. You know that if we try to understand, if we try to calculate the area under any process line in TS plane, that gives directly the heat transfer, heat exchange, that we have studied in our thermodynamics, and that is from second law. So, basically if we can map all the processes in TS plane, and if we try to calculate the area under any process line in TS plane, that gives us the heat interaction. So, now say let us assume that the pressure is like this. So, this is the pressure, say this is P ATM, and if we consider, so this is, let us say this is V this is V, and this is V BDC, and say this is V TDC. So, piston is having movement between these two locations, that is V BDC and V TDC, that is what we have seen in the last figure. So, this is when piston is at BDC, the volume corresponds to V BDC. When piston is at TDC, the volume of the gas or volume inside the cylinder is the V TDC. Now, we can map the processes. So, first process is intake. So, maybe piston is at BDC and is coming to VDC, and this is the process. So, let us say this is process, this is point 1, and then it is coming to 2. So, piston comes here. So, this is the process. Constant pressure is constant because you know this is a constant pressure process, volume is changing, and what is the pressure? Pressure is the atmospheric pressure. So, basically I mean though we can say, because we should have some pressure difference between the atmospheric pressure and pressure inside the engine cylinder, and that is the driving force, but so it can be approximated as the constant pressure intake process. And then when piston is at 2, the next process is compression process, that is the compression stroke. Then you know this is coming to, let us say, point 3. So, piston is again coming back from BDC to TDC. So, the press charge is getting compressed, and this process can be approximated as an isentropic process. Now, I will be coming to that point, and then when piston is at TDC, what we have discussed that say this is 0.4. So, spark plug switch will be on and combustion will be initiated and will be completed, and it is because of this combustion pressure and temperature inside the cylinder will be high. So, you can see that pressure increases, but the volume is remaining constant more or less. It is assumed that the entire combustion will be completed when piston is at TDC. So, it takes a very less time and it is approximated as a constant volume heat addition, that is the combustion process. And finally, piston comes from TDC to BDC again, following this isentropic process. We are assuming that the process is isentropic, that is there is no heat interaction between the system and the surroundings, and that too it is frictionless process. So, I will tell you, because these are approximated processes. So, 4 to 5, and finally, when piston is at BDC, when piston is at BDC, basically exhaust valve is allowed to open and momentarily certain amount of combustion gases which are there inside the cylinder at a high pressure will leave out, and when the combustion gases are coming out from the engine cylinder, they are carrying certain amount of enthalpy, certain amount of energy. So, that is basically exhaust. So, certain amount of combustion gases will leave out from the combustion chamber or engine cylinder, and it will take certain amount of heat. So, heat loss. So, that process is also known as constant volume heat rejection. So, say 2,6. So, basically this is the constant volume exhaust. So, as if certain amount of heat is getting rejected from the system, that is from the engine cylinder at constant volume. So, momentarily when piston is at BDC, exhaust valve is allowed to open and certain amount of combustion gases will leave out. So, this is the constant volume heat rejection process. Now, if we try to map all these processes in TS plane. So, now when piston is again coming from TDC, that is BDC to TDC to complete the exhaust. So, when we open the exhaust valve, momentarily certain amount of combustion gases will leave out, that is true, but eventually you need to clear all the gases that those are there inside the cylinder, and piston will come from BDC to TDC, and that process is 6 to 1 to complete the cycle, right. Try to understand. I would like to tell you one important point over here, that process 1 to 2 and 6 to 1, these two processes are same and they are same thermodynamically, they cancel each other. So, while analyzing SI engine or the cycle, we can analyze keeping the processes 1 to 2 and 6 to 1 left up from the figure. It is not necessary that we have to analyze the cycle considering these two processes, because these two processes are thermodynamically same. So, they cancel each other. So, if we can consider that, it is convenient to represent only the processes 2 to 3, 3 to 4, 4 to 5 and 5 to 6 or 5 to 2, because points 2 and 6 are same. So, let us 2 to 3 that we have approximated isentropic process, and then, so this is 2, this is 3, then 3 to 4 you can see the temperature will increase. 3 to 4 is, you can see that it is 3 to 4 is constant volume heat addition, that is combustion process. So, pressure has increased from P3 to P4, temperature also will increase, and that is reflected over here. And finally, four to 5 is the expansion, and it is because of this expansion temperature of the working substance and pressure will reduce, and that you can see from both these diagrams. And finally, 5 to 2 or 6, because I am not going to write 6, 5 to 2 the 5 to 2, that is constant volume, 5 to that is constant volume heat rejection, that you can see that the temperature will reduce. So, T2 is less than T5. So, these are the PV and TS plane. Now, if we try to analyze the performance of the SI engine, so let us discuss certain issues. What are those? You know, we have discussed that to analyze this cycle, to analyze the performance of SI engine, these cycles which are having 4 different processes are compared with an air standard cycle, and that cycle was invented first by Nicholas August Otto, and that is known as Otto cycle. So, basically we are trying to compare all the processes which constitute together to form the cycle of SI engine can be approximated with an air standard cycle. So, when you are trying to analyze all the processes by using an air standard cycle, we can assume that the working substance even what is there for the SI engine as an ideal gas. So, we are considering working substance to be an ideal gas for the analysis, and it is due to the fact that we are assuming that the cycle is approximated by an air standard cycle. So, if we assume that it is not purely air, it is air fuel mixture, that is during the compression stroke. Again, for the expansion stroke, it is not only purely air and fuel, rather it is several components of the combustion products. So, combustion product. So, what we can write, we are assuming that air standard cycle. So, for air standard cycle we will be using several ideal gas relationship. I am just listing them down because we will be using those to analyze this cycle. So, we know that PV equal to RT, and it is better because for while we are trying to analyze, it is better to analyze per unit mass of the working substance, that is in a specific using the specific volume. So, PV equal to MRT, then we can use P equal to rho RT, we can use DH equal to Cp dt. As I told, we are using specific quantities, it is better to analyze per unit mass of the working substance. Du equal to Cv dt, because we have studied about all these in our basic thermodynamic course, and we also can write that that is P v to the power k equal to constant. We also can write T v to the power k minus 1 equal to constant. We also can write T p to the power 1 minus k upon k to the power equal to constant. Okay. So, we can write all these expression, right. So, we have written, we will be using all these expressions while analyzing the SI engine performance. Now, let me introduce here one term that is very important. You know that piston is having essentially movement between these two locations, that is BDC and TDC. So, when piston is at BDC, volume of the cylinder, the volume corresponding to that other, I can say when piston is at BDC. So, this is VBDC, right. Volume of the working substance is VBDC. When piston is at TDC, volume of the working substance is VTDC. Now, the ratio of these two volumes VBDC by VTDC is known as the compression ratio of the engine. So, this is the compression ratio. So, when piston is at VDC, volume is VBDC. When piston is at TDC, volume of the working substance is VTDC. Ratio of these two volumes is known as the compression ratio of the engine. So, VBDC by VTDC is RC. We also can write VBDC by Vt dc equal to Rc. So, this Rc is compression ratio. Okay. Okay. So, now if we go to do the mathematical analysis for the quantification of thermal performance. So, let us first consider process 2 to 3, because we are not going to consider process 1 to 2 and 6 to 1, as I said. These two processes are thermodynamically same, so they cancel each other. So, process 2 to 3, let us first consider process 2 to 3. Process 2 to 3. What is this process? Process is isentropic compression. So, there is no heat interaction, frictional effect is neglected, because let me tell you one thing, those are basically basically kind of not the ideal process, but we are trying to approximate essentially to quantify the thermal efficiency. In reality, frictional effect will be there, and also we cannot really prevent heat loss, but we can tell that these assumptions are not very bad assumptions, and as if the process is not violating severely from the isentropic process. So, the process is not deviating from the isentropic process severely. So, now if we write it for the isentropic process, so what we had seen that Q23 or Q23 equal to 0, no heat interaction, while this W23 equal to P3 V3 minus P2 V2 by 1 minus K, that is R T3 minus T2 divided by 1 minus K. Now, I would like to tell you one important thing. See, this is the expression of work done, because this is work which is done on the compression, on the mixture. So, basically if we try to write the first law of thermodynamics applied to a system, it is not for a flow system, that is first law of thermodynamics for a non-flow system, for the cyclic process, then we can write this del cube equal to du plus del w. Okay. So, this is in the specific form we can write del cube equal to del u plus del w. So, this is 0, there is no heat interaction. So, we can write that W223 because this is this W223. You also can write W223, that is the convention only, writing convention using different style. So, it is what we can write, that is if we integrate u2 minus u3, right. So, this is u2 minus u3. Now, issue is this is the work done. So, we can get it using this ideal gas equation, and we have also seen that it can be written in terms of the internal energies. So, this is u2 minus u3. So, we can write that is equal to u2 minus u3, right. So, this is the work done. Next process is, if we go to the slide, process is 3 to 4. So, that is the constant volume heat addition that mimics the combustion process in practical applications and in reality. So, we can write process 3 to 4 constant volume process. So, work done is 0. So, basically W3 to 4 equal to 0. What about Q34? So, Q34 equal to M constant volume process. So, CV T4 minus T3. What about M? See, this M is, you know, that mass of air plus mass of fuel, that is the mass of the mixture, it should be MM mixture. So, if you try to write in the specific form, then we can write Q324 equal to CV into T4 minus T3. So, this is very important. I am putting this quantity in a box. Okay. Next process is, if we go to the previous slide, next process is 425. This is again isentropic expansion, that is the power stroke, right. So, if we write here process 324, so this is constant volume heat addition, that is the combustion process. Similarly, process 2 to 3 is isentropic compression. Okay. So, process 3 to 4 is fine. Next is process 4 to 5. So, we can write process 4 to 5. So, this is again isentropic expansion, that is the power stroke. So, I am not going to write again whether the valves will remain closed or open, because you know. So, this process is power stroke, both valves are remaining closed, power stroke. So, what about the this isentropic process? So, no heat interaction. So, basically we can write Q 425 or Q 425 equal to 0, right. What about W 425? It would be, you know, it is very important. You can try to understand that it would be P5 V5 minus P4 V4 divided by 1 minus K, that is R T5 minus T4 divided by 1 minus K, right. So, that is what we can write. So, that is in terms of internal energies. So, that is U4 minus U5. So, we can write CV into T4 minus T5. So, this is T4 minus T5. Okay. Because del Q equal to du plus del W, this is equal to 0. So, W 425 will be equal to W 4 minus sorry U4 minus U5, and that is nothing but C5 into T4 minus T5. Similarly, you know, here also we can write this is equal to CV into T2 minus T3, right. Okay. So, we have written process 4 to 5 again. So, we are left with the last process, that is process 5 to 2, right, because this is the blow down. So, constant volume blow down. So, immediately after opening the exhaust valve, though the piston is remaining at VDC, certain amount of combustion gases will come out from the engine cylinder and those gases will carry certain amount of energy. So, I mean as if heat is getting lost. So, this is the Q out and this is Q in. So, as I told you that you can directly get it from the area under the process line in TS plane. Okay. So, what we can do? We can next calculate the process 522. So, process 522, I am not going to write 6 because it is these 2 points are same. Or 526. So, this is the process is constant volume heat rejection, some books it is written blow down, constant volume process. So, W 522 or W 526 equal to 0, but we can write cube 522 or cube 526 equal to m of mixture Cv into, this would be equal to if we go to the previous slide, so this should be T6 minus T5 or T2 minus T5. We can write T2 minus T5 or Cv into T6 minus T5, same because T2 equal to T6. Okay. So, in the specific form cube 522 or cube 526 is Cv into T2 minus T5 or Cv into T6 minus T5. So, we have, I am again making or keeping this quantity in a box. I am writing, so this is basically heat rejection, right. If we go to the previous slide, so that is basically heat addition. So, we are supplying this heat to the cycle through the combustion and we are supplying fuel, right. While out of this heat being supplied to the cycle, you can understand this is the amount of heat is going to be rejected. So, this is not the useful heat. So, you can understand that we are not able to utilize the heat totally. So, certain amount of work that we will be getting from this process is not equal to the input energy. So, definitely we can define thermal or thermodynamic efficiency of the cycle. So, if we write the thermodynamic efficiency of the cycle or thermal efficiency of the Otto cycle, say eta auto equal to W net by Q in, that you have studied in thermodynamic course. So, we can write in again specific form, that is Q out divided by Q in, right. So, or W net divided by Q in. So, from there we can write it. Now, what is Q out? That is the heat is being rejected. So, we can write that is 1 minus per unit mass we have tried to calculate. So, that is Cv into T2 minus T5, right. So, we can straightway write Cv into T2 minus T5. So, we can write it Cv into T2 minus T5, whereas because we are not going to write 6, because this is T2 equal to T6, and what is heat in, that is Q in, Cv into T4 minus T3, Cv into T4 minus T3. We can do some algebraic manipulation and we can write it. So, if we go to the next slide, so eta auto equal to 1 minus we can write it 1 minus T5 minus T2 divided by T4 minus T3, right, T4 minus T3. So, we can write 1 minus T2 upon T3 into T5 upon T2 minus 1 divided by T4 by T3 minus 1. So, now I will be doing one important analysis. So, what we can write here is, you know, what is T2 by T3, that is V3 by V2 to power k minus 1. That is, in the beginning I had written, if we go to the previous slide and I had listed down these expressions, I had listed down all these expression of ideal gas expression, ideal gas relations. So, Tv power k minus 1 is equal to constant. From there we can write it T2 by T3 equal to T2 by T3 equal to V3 by V2 power k minus 1. Okay. Now, try to understand, if we go to the PV plane. So, this V3 equal to V4 and V2 equal to V5, right. V3 equal to V4 equal to VTDC and V2 equal to V5 equal to VBDC. So, I can write this, V3 equal to V4 and V2 equal to V5 power k minus 1, and this is again nothing but T5 by T4. So, T2 by T3 equal to T5 by T4, we can write therefore, T5 by T2 equal to T4 by T3. So, this is say one equation. If we use this equation T5 equal to T2, T5 by T2 equal to T4 by T3, you can see this will get cancelled. So, the quantities both in numerator and denominator will get cancelled, and then we can write 1 minus T2 by T3, right. So, what is T2 by T3? That is V3 by V2 power k minus 1. So, that is 1 minus V2 by V3 by V2 power k minus 1. I have already defined one term today. If we go to the previous slide wherein I have defined this term is this: compression ratio is VBDC by VTDC. Just try to remember, the compression ratio is the ratio which is defined as the ratio of which is defined as the ratio of VBDC to VTDC. So, when piston is at BDC, the volume to the volume when piston is at TDC. Now, for this particular case, when V3 equal to VTDC and V2 equal to VBDC. So, for this case RC equal to VBDC by VTDC. So, that is equal to V2 by V3, that we can write from here. That is also equal to V5 by V4. So, V2 by V3 equal to RC, that we should remember now. If we go to the slide, V3 by V2 equal to then 1 upon RC. So, we can write eta auto equal to 1 minus 1 upon RC power k minus 1, because V2 by V3, that is RC, that we have defined just few minutes back. Let me go to that slide again. V2 by V3 equal to RC, right. So, V3 by V2 would be 1 upon RC. So, we have written. So, that is very important. Efficiency of the Otto cycle can be written, this is 1 minus 1 upon RC power k minus 1. So, if we box this, if we put this quantity in a box, so this is the mathematical expression of the thermal efficiency of Otto cycle, right. So, thermal efficiency of the Otto cycle can be expressed in terms of the compression ratio. So, try to understand, higher the compression ratio, higher will be the efficiency, right, but that is within the range of a certain value. So, even for the SI engine, compression ratio is fixed, and using within working within this particular range, if we increase the compression ratio, efficiency of the Otto cycle will increase. Okay. So, what we can write is now that if we go to the next slide, if we try to plot, so this is RC and this is eta auto. So, if we start from 1, 2, 3, 4, 5, 6, say 1, 2, 3, 4, 5, 6. When RC equal to 1, then thermal efficiency is eta 1, eta when 0. So, you can understand that if we start from here, it varies like this. So, this is the variation of thermal efficiency of Otto cycle versus the compression ratio plot. What we can understand, if we increase the compression ratio, efficiency increase, So, if we summarize today, we have discussed about several processes which are important to analyze the SI engine, and we have mapped all those processes in two different thermodynamic planes. We have compared all the processes by using an air standard. I mean, all the processes, those processes constitute together to form a cycle, and that cycle we have compared by using an air standard cycle, which is the Otto cycle. German engineer Nicholas August Otto who first invented this cycle, and from there using the air standard equation we have tried to quantify the thermal efficiency of Otto cycle, and we have seen that the thermal efficiency of the Otto cycle can be written in terms of the compression ratio of the engine. Higher the compression ratio, efficiency will be higher within the working range of the or allowable range of the compression ratio of SI engine. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.